This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Our next illustrated example features a 50-volt source in parallel with R1, a 1 kΩ resistor, and R2, a 1.4 kΩ resistor. We're again being asked to solve for the voltage drop across each element, the current through each element, the power dissipated by each element, the source current, and the total power. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Let's go about the analysis of the circuit in a different method. First, voltage across elements in parallel is the same. E equals V1, which equals V2, and they all equal 50 volts. Source current equals I1 plus I2. Let's start by combining these elements in parallel, which yields a total resistance of roughly 583.3 ohms. Using this simplification, we can solve for source current, where source current is equal to supply voltage divided by total resistance. Substituting in our given values yields 85.7 milliamperes. Total power is equal to supply voltage times source current. Substituting our given values yields a total power of 4.3 watts. We can now use this data to solve for electrical properties of individual elements. Incoming current is known for a parallel combination of two known resistors. This is a perfect setup for the current divider rule. The current divider rule applied to resistor R1 demonstrates that I1 is 50 milliamperes. An algebraic rearrangement of the Kirchhoff's current law equation for this circuit demonstrates that I2 is the remaining 35.7 milliamperes. An application of Ohm's law confirms this result, where I2 is indeed 35.7 milliamperes. P1 equals V1 times I1. Substituting our given values yields 2.5 watts. An algebraic rearrangement of the power equation demonstrates that P2 is the remaining 1.8 watts. As a means of checking our work, V2 squared over R2 does indeed yield 1.8 watts. I've got a reasonable degree of confidence our answers are correct, and we can move on to the next illustrated example. Our next illustrated example features a 36-volt source in parallel with R1, a 300 ohm resistor, R2, a 500 ohm resistor, and R3, also a 300 ohm resistor. We're again being asked to solve for the voltage drop across each element, the current through each element, the power dissipated by each element, the source current, and the total power. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Again, for the sake of variety, let's just go about this analysis slightly differently. The parallel combination of these three resistors represents a total resistance of roughly 115.4 ohms. Source current is equal to supply voltage divided by total resistance. Substituting our given values yields 312 milliamperes. Total power equals supply voltage times source current. Substituting our given values yields 11.2 watts. We now know source current coming into a parallel configuration of three elements. Ordinarily, we could use the current divider rule. However, the current divider rule is a special case scenario for only two parallel elements. Let's again simplify this circuit by taking the parallel combination of R1 and R3, both 300 ohm resistors, into a single resistor I'm calling R single prime, and R single prime is in parallel with R2. The parallel combination of R1 and R3 is 150 ohms. We now have a perfect setup for the current divider rule. Incoming current is known, and it's a parallel combination of two known resistors. Where source current splits into two paths, I'm calling I single prime plus I3. The current divider rule set up to solve for I single prime yields 240 milliamperes. R single prime is actually the parallel combination of two identical resistors. If 240 milliamperes enters a parallel combination of two identical elements, we should find current splits through them evenly. I1 equals 120 milliamperes, as does I2. An algebraic manipulation of the Kirchhoff's current law for the second simplification demonstrates that I3 is I source minus I single prime. Substituting our calculated values yields the remaining 72 milliamperes. The power delivered to identical resistors R1 and R2 is equal to the voltage across them times the current through them. Substituting our given values understandably demonstrates that P1 is 4.3 watts, as is P3. An algebraic manipulation of the power equation demonstrates that P2 equals P total minus P1 minus P3. Substituting our given values yields the remaining 2.6 watts. All right, let's move on to our final illustrated example. Our last illustrated example features three current sources, one at 30 milliamperes, one at 50 milliamperes, and one at 20 milliamperes, in parallel with two resistors, R1 at 390 ohms and R2 at 750 ohms. For this last example, We're only being asked to solve for the voltage drop across each element and the current through each element. Now, before you rush off to perform your analysis, make sure to note the direction of travel for these current sources. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Current sources in parallel add up. 30 plus 50 minus 20 yields a current source of 60 milliamperes. This 60 milliampere current source is in parallel with R1 and R2. This is again a perfect setup for the current divider rule. Incoming current is known for a parallel combination of two known resistors. The current divider rule set up to solve for I1 yields 39.5 milliamperes. An application of Kirchhoff's current law demonstrates that I2 is the remaining 20.5 milliamperes. Finally, an application of Ohm's law demonstrates that voltage across resistor 1 is 15.4 volts. By extension, all elements in this parallel circuit must also experience a 15.4 volt differential. Alright, that's it. In conclusion, this lecture examines several illustrated examples of parallel DC circuit analysis. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.